Hi everybody, this is Miss Bufford and this is video 3 in our acids and bases unit, and this video covers pH and pOH scales. In this video, your learning goals are to be able to define pH and pOH. So what is pH? pH is a scale used to determine the concentration of hydronium ions in aqueous solution. This tells us how acidic or how basic a solution is. The numbers representing each pH value are a simplified way to think about the hydronium ion concentration. This is a logarithmic scale, meaning that each number represents a tenfold change in the concentration or the amount of hydronium ions in solution. We're going to come back and talk about what that last part means in a little bit. pOH is a scale used to describe the concentration of hydroxide ions in aqueous solution, and just like the pH, this can tell us how acidic or basic a solution is. The numbers representing each pOH value are a simplified way to think about hydroxide ion concentration. This is also a logarithmic scale, meaning that each number represents a tenfold change in the concentration or amount of hydroxide ions in solution. So a lot of us are probably already familiar, or at least we have an idea, we've heard of the pH scale, or we've used it in some way in our lives. If you have a swimming pool, then the test kit that you use to test the pH of your pool, uses the pH scale to measure how acidic or basic your pool water is. And if we take a look at this picture right here in the middle, you can see the pH scale over on the left, and it starts with 0 and goes all the way down to 14. And then if you look at the pOH scale over on the right, you'll notice that it looks like it starts at 14 and goes down to 0. So basically it looks like these scales are opposite from one another, where a 0 on the pH scale corresponds to a 14 on the pOH scale. And then all the way at the other end of the scale, a 0 on the pOH scale corresponds to a 14 on the pH scale. So the pH and pOH scales, they're opposite. So why is that? We're going to answer that question on the next slide. All right, why are the pH and pOH scales opposite from one another? To start answering this question, I'm going to first talk about the autoionization of water. And what this means is that to a small degree, water molecules in a pure sample of water are going to self-ionize, meaning they're going to split into hydrogen ions and hydroxide ions. And again, this only happens at very, very small concentrations, so maybe 1 in 10 million water molecules will autoionize. When water molecules autoionize, they're creating equal numbers of particles. So we'll have 1 hydrogen for every hydroxide that's formed, meaning they exist in equal concentrations. And since these concentrations are equal and very low, then we can still say that water is a neutral substance. And so we're going to visualize this by looking at these beakers over here. And if you look at the beaker in the middle where I have the hydronium ions equal to the hydroxide ions, you'll see that the particles in there, the red ones represent hydronium, and the blue ones are going to represent our hydroxide ions. They exist in that beaker in equal concentrations. Okay? Now, if I wanted to change the ratio of hydrogen ions or hydronium ions to hydroxide ions, then I'm going to have to add something to that solution. If I wanted to increase the hydronium ion concentration, then I'm going to have to add an acid to that substance, or a substance that's going to dissociate and release hydrogen ions into that solution. And if I do that, let's say I'm moving to the beakers, through the beakers over to the left, where the pink ions are getting more and more abundant. If you notice that the concentration of hydronium ions does increase as we move through those beakers. And if you'll notice also that the concentration of hydroxide ions in each beaker is getting smaller and smaller as you move farther and farther over to the left. And the reason for this is, as that concentration of hydronium ions increases, it's more likely that those hydronium ions will come into contact with one of those hydroxide ions and pull it out of solution by reacting with it to form a neutral water molecule. And so the higher the concentration of hydronium ions, naturally the lower the concentration of hydroxide ions is going to become. And is the same as true for the other end. So if we start in the middle beaker again, where hydroxide and hydronium are in equal concentrations, let's say this time I want to increase the concentration of hydroxide. And so if I wanted to do that, then I would have to add a base to this solution, something that is going to dissociate and release hydroxide ions. If I do that, and moving through the beakers over off to the right now, you'll notice that the hydroxide ions, or the blue particles, are getting more and more abundant in each beaker, and the hydronium ions, or the red particles, their concentration is dropping as the hydroxide ion concentration increases. And that's for the same reason. We have tons and tons of hydroxide ions in solution and just, a small amount of hydronium ions, and as those hydroxide ions concentrations increase, they're going to be reacting with any hydroniums they come into contact with to form neutral water molecules. And so that is why the pH scale and the pOH scale run opposite from one another, because naturally as one increases, it's going to cause the other to decrease. Okay? All right, so where do the numbers on the pH scale come from? And how can a single number represent a tenfold change in concentration? So to answer this question, we're going to use these 4 cups over to the right. Each one of these cups contains exactly 1 mole of hydronium or hydrogen ions in different volumes of solution. So let's take a look at the volumes in here first before we calculate those concentrations. So if you notice, this first cup has 10 liters, the second cup has 100 liters, then 1,000, and then 10,000. And so each one of these cups, its volume increases by a factor of 10. So 10 times 10 is 100 times 10 is 1,000, and 1,000 times 10 is 10,000. So that's an important observation to make here. So let's go ahead and calculate the concentration of hydrogen or hydronium ions in each one of these cups. All right, so now I've calculated the concentrations, and remember in chemistry we use molarity as concentration. And so here I can see that as I move down from one cup to the other, my concentration gets smaller and smaller and smaller. And if we kept going, it would get even smaller. And in chemistry, it's really common to deal with really tiny concentrations of hydrogen or hydronium ions. And so in order to make these a little easier for us to deal with as far as calculations and thinking about the numbers themselves go, we're going to go ahead and write these in scientific notation. So here they are written in scientific notation. And what I'm going to do next is I'm just going to put up the pH values that correspond to each one of these cups. I haven't done any special calculations so far to get these. I'm just putting them up here because I want you to pause the video and just take a minute to compare the pH values to the numbers that we've written in scientific notation here. Okay, so hopefully you paused the video and you were able to see that the pH values are actually equal to that absolute value of that exponent there. So if our concentrations all begin with 1.0, then our pH values are going to be equal to that absolute value of that exponent right there. So that's pretty easy, right? So we can see how each pH value might represent or does represent a tenfold change in the concentration of a solution, because it's really just telling us how many places we had to move that decimal in order to get that number into appropriate scientific notation. Okay, so on this slide I have a lot of numbers, and I also have a diagram that's going to kind of help give us a visual on what's happening with the concentration of different ions as our pH is changing. So if you take a look over here, you can see that just like we did on the previous slide, I'm calculating the concentration of hydrogen ions for every pH value on our pH scale. And you'll notice if you look in the second column labeled hydrogen ion concentration, our concentration starts off at 1, being the most concentrated solution with a pH of 0. And as we move down, it gets less and less concentrated until we get all the way down here to a pH of 14. the very tiny hydrogen ion concentration. So what I've done is I've taken these numbers from the pH scale and I've put them on the diagram that we used to talk about how pH and pOH, what their relationship is. And so if you take a look here, 0 corresponds to that beaker that has a really high hydronium or hydrogen ion concentration, and 14 is actually corresponding to the one that has the smallest hydrogen ion concentration, but the largest hydroxide ion concentration. And the only way that we can produce something that has a pH of, greater than 7, a more basic pH, is to add a base. And so it's very common for people to just use the pH scale and kind of ignore the hydroxide or the pOH scale, even though it does exist. So when we're talking about pH, the numbers that are smaller, less than 7, are going to represent our more acidic solutions, or solutions that have higher hydronium ion concentrations, with 7 being our neutral point. And then numbers that are larger than 7 are going to represent more basic solutions, or solutions that have a higher hydroxide ion concentration. Right, so now let's go ahead and look at hydroxide, or the pOH scale. Okay, so here's the same thing we just looked at for pH, but now we're going to look at it for pOH. And if we take a look at our pOH scale, we notice I just have this set up so that it runs, the pH and the pOH correspond to each other how they normally would. So we're starting with 14 at the top and going down to 0. But if we take a look over at our hydroxide ion concentrations, we'll notice that pOH of 0 corresponds to that more concentrated solution of hydroxide ions with a 1. And then as we move up on the pOH scale, then our concentrations are getting smaller and smaller. And again, just like with pH, the numbers from the pOH scale are going to come from the exponents on the concentrations of hydroxide ions when they're written in scientific notation. Okay, so if we take a look at this diagram over here, we just talked about the top part. Now I've put up here the pOH scale, and you can see it running opposite to the pH scale, where 0 on the pOH scale down at the bottom is corresponding to that beaker that has the really high concentration of hydroxide or blue particles in it. And as we move to the left, it's getting more and more acidic. So what this is showing you is that smaller pOH values, so values on the pOH scale that are less than 7, are going to represent higher concentrations of hydroxide ions and more basic solutions. And then larger pOH values, or pOH values that are greater than 7, are going to represent higher concentrations of hydronium ions and more acidic solutions. Okay, with this last slide, we're just going to kind of go ahead and recap all of the ideas that we've talked about in this video. And we're going to start over here with a little equation that shows water ionizing. So remember that water is going to naturally ionize into hydroxide and hydrogen ions, or hydronium ions, in very small amounts. But these ions, when they're created after these water molecules dissociate, are going to exist in equal concentrations. And so that's why we still consider water to be neutral. Now, if we wanted to change the ratio of hydrogen to hydroxide ions, let's say we wanted to increase our hydronium ion concentration, then we would need to add an acid to that solution, or a substance that's going to release hydrogen ions, so that we can have more hydrogen ions than hydroxide ions. Remember, the higher the hydronium ion or hydrogen ion becomes in a solution, the more of those hydroxide ions are going to be pulled out of solution, because they're going to be reacting with those hydrogen ions to form neutral water molecules. And so that's why our hydroxide ion concentration gets really small once we have an excess of hydrogen ions or hydronium ions. Now, on the other end of the scale, if we wanted a more basic solution, then we would have to add a base to our aqueous solution, or something that's going to dissociate to release hydroxide ions. And remember, as our hydroxide ion concentration becomes larger and larger, then our hydronium ion concentration is going to drop because now we've got an excess of hydroxide ions that are going to be reacting with those hydronium ions to form neutral water molecules. And so naturally, we have a high concentration of hydroxide. We're going to have a low concentration of hydronium or hydrogen ions. Now, looking more at the pH scale and the pOH scale, more acidic conditions are going to be represented by smaller numbers on the pH scale and larger numbers on the pOH scale. And then more basic conditions are going to be represented by larger numbers on the pH scale and smaller numbers on the pOH scale. I hope this video was helpful. Thank you for watching Buffered Chemistry. See my practice calculation videos for examples of how to do calculations for pH, pOH, hydrogen ion concentration, and hydroxide ion concentration. And don't forget to subscribe to my YouTube channel for more chemistry help.